Hey guys, in this video I just want to show you my way of solving the Gaussian integral. This is arguably one of the most famous integrals of all time, and it makes sense why. So the graph of this looks something like this. That was a horrible graph. These should really be horizontal asymptotes at the end here. And we are trying to find this area from negative infinity to infinity. So the first thing I'm going to do is let this integral be called I. Okay? And then I'm going to square I. So that I squared is the integral from negative infinity to infinity of e to the negative x squared dx. Integral negative infinity to infinity of e to the negative x squared dx. Alright. Then, my next step is to put a dummy variable here, and I'm just going to let that dummy variable be y instead of x. So replace x with y, because it's technically the same value. So this becomes the integral from negative infinity to infinity e to the negative x squared dx. Integral negative infinity to infinity e to the negative y squared dy. Now, using properties of double integrals, I can rewrite this as the integral of negative infinity to infinity, integral negative infinity to infinity, of e to the negative x squared, e to the negative y squared, dx dy. Now, notice I can write this as the integral negative infinity to infinity, integral negative infinity to infinity of e to the negative x squared plus y squared, right? Dx dy. Now this is where this problem gets complicated. So from this step on, this is more advanced multivariable calculus stuff, but we are going to have to go into the polar world. So we know that x equals r cos theta and y equals r sine theta. So then x squared plus y squared equals r squared cos squared theta plus r squared sine squared theta, which equals r squared times cosine squared plus sine squared. But we know sine squared plus cosine squared equals 1. So that means x squared plus y squared equals r squared. So now I have I squared equals the integral from negative infinity to infinity, integral negative infinity to infinity, of e to the negative r squared dx dy. Now I have two problems. What this integral represents is the volume under the surface. We're not talking about the area under a curve anymore. We're talking about the volume under a 3D surface. And this right here represents the area sectors. But now I'm in the polar world. So in the regular world, dA was equal to dx dy. But now I have to figure out in the polar world, what's it equal to? And there's this thing called Jacobian's Constant. And basically what this does is it's multiplied by dr d theta. And this, in the polar world, is actually a sector area. Because in the polar world, you have to think about how this graph looks. We're really taking sectors and forming something. So this is the sector area, r dr d theta. So now I get I squared equals the integral. And now I also have to change some of my bounds. So when thinking about this 3D graph, this graph is actually coming out at me starting at 0. But it's coming out at me for an infinite amount of time and space. So this is the integral from 0 to infinity. And then we're also rotating this about the plane 2 pi radians to form it. So this is 0 to 2 pi of e to the negative r squared r dr d theta. Now what I'm going to use is a u substitution here. Let u equal r squared, so that du dr equals 2r and dr equals du over 2r. I can bring that 1/2 out to get I squared equals 1/2. Integral 0 to infinity. Integral 0 to 2 pi of. Now, this is going to become, my r's will cancel out, right? And this is e to the negative u du d theta. Now, I forgot to mention that these bounds should be switched. I got them mixed up. This one should be 0 to 2 pi, the first one. And this should be 0 to infinity. So now I get I squared is equal to 1/2 integral 0 to 2 pi. And now this is going to become negative e to the negative u from 0 to infinity d theta. Now when I evaluate this, that's negative e to negative infinity minus negative e to negative 0. And this is equal to 0 minus a minus 1, which is really 0 plus 1, which equals 1. So now I get I squared equals 1/2 integral 0 to 2 pi of d theta. And this is going to be I squared is equal to 1/2 bracket theta. That's the integration there. 0 to 2 pi. I squared equal to 1/2 times 2 pi minus 0. And therefore, I squared equals pi. Wow, we're done. But no, we are not. We are not. We set I to be the integral of e to the negative x squared dx from negative infinity to infinity. So look at how simple this is. What if I just take the square root of both sides? I get I equals the square root of pi. Bam. So therefore, the integral from negative infinity to infinity of e to the negative x squared dx equals the square root of pi. And that is arguably the most famous integral to ever exist. And it uses a very simple manipulation, and it's quite interesting that this area is exactly the square root of pi.